following on from some of the early videos, we got to this stage here. We got to this stage here where for all small n beyond capital N, it must fall within this interval here. Within this interval here. So this level here is your limit, your rho. This level here is your rho plus epsilon, also known as r. So you can think of this level here as being rho plus epsilon, or you can just think of it as r. Okay, so the point is that for all small n beyond capital N, it must fall within this interval here. So we got to this stage here, and then so now let's just ignore this bit here. Let's just ignore this bit here. Okay, so looking at this and this, so times both sides by an, so that will then give you this an plus 1 less than the common ratio times an. So what it's saying is that if you get your current term times the common ratio, then your next term will be less than your current one. So the next term will be less than your current term times the common ratio, and then you can repeat the process. So if you look at this here, so beyond capital N, a capital N times that common ratio, this r here, times that common ratio, then this will be greater than your next term. And then if you repeat the process, so if you look at this here, an plus 1, which is your next term. So your next term here, what's in here is really r times an. And then don't forget, so this is r times an, just this bit here. And then you've got it times r again. So the point is that if you continue the process, then this will be r squared, because each time you're multiplying by r, because it's saying get your current one times r, and then your next one will be less than that. And then if you repeat the process again, this bit here will have already contained r in there, r. So here you've got your r a n just in this bit here, and then you've got to times this r again here. So that's why you've got r squared here. The point is, if you keep on multiplying by r times by r, it just gets smaller and smaller and smaller. So each term it will get as you go on and on and on, it will just get smaller and smaller and smaller, because you're timesing by r again and again. Each time you're multiplying by r. Don't forget r is less than 1. So what's happening here is that you've got r squared, r to the power 3, r to the power 4, and so on. This here is really your geometric sequence. Your geometric series. Well, we've already seen that if you have a geometric series where the common ratio is less than 1, then we've already seen that a geometric series with a common ratio less than 1, then it's going to converge. So therefore, well, your geometric series is always greater than it's always greater than your an. Then because your geometric series, well, we know that the geometric series will converge when the absolute value of r is less than 1. So therefore, what you're trying to investigate, this an here, this series here will also converge, because the geometric series is always greater. The geometric series is always, have a read of this. The geometric series is always greater or equal to what you're trying to investigate. So if your geometric series converge, then the series that you're trying to investigate must also converge. Okay.